on time domain analysis of noise. So with this section, really what we want to do is just introduce some basic concepts about noise that we're going to be using later on, and make some basic definitions that are going to be very important as we go forward in this section on noise. Now at first glance it may seem almost impossible to do any kind of analysis on noise in electronic circuits. I mean, after all, we can say very little about the precise value that a noise voltage or current is going to take on at any point in time. That's the whole point. It's a stochastic process. So if we don't know the value of a noise or current, how can we do any kind of time domain analysis on it? Well, hopefully, like all random processes, what we can do is say something about the statistics of that noise quantity. So I want to start out here with a basic definition. Something you've probably encountered already is to define the root mean square value of a noise quantity. So pictured here in this graph is just a typical example of a random noise signal. It's bouncing all over the place over time, but within a window, in this case from 0 to 1 second, we can integrate the squared value of this quantity. And taking the square root of that, we get an estimate for the root mean squared value of that noise. Now, if we assume that whatever's giving rise to this noise is a stationary random process, then that means its statistics are not going to change over time. So we can use any window for integration here. We can integrate it from 0 to 1 second or 1 to 2 seconds. We can integrate from 0.5 to 1.5 second. Any window we choose should give the same expected value for that integral. So if it's a voltage, what we end up with then is a root mean squared voltage quantity. By taking the square root, we get something that dimensionally has units of just volts. And what it's good for is that the physical interpretation of the RMS value is it's the voltage that, if applied across a 1 ohm resistor, we'd get that many watts of power being burned in the resistor. Okay, so that's one way to think of it. It's sort of like the average power, if you like, in that noise. But power doesn't really have units of volts; it has units of watts. So we would have to take those, those volts and apply it across a resistance to get some power. Similarly, we can make the exact same definition with a noise current. We're going to encounter both noise voltages and noise currents in circuits in general. So we can take the current in any branch of a circuit, plot it versus time. If it's a noise current, it's just going to bounce around all over the place. But if it's a stationary random process, then we can integrate over a window and estimate its root mean square quantity that way. Naturally, the longer the window of integration you take, the more accurate that estimate of the RMS value becomes. This assumption of stationarity, you might be wondering, how real is that? Of course, it's an approximation. There's nothing no random process that's stationary for all time. Sooner or later, the circuit gets turned off, or the temperature may change somewhat, which will change the noise statistics in general. Or something's going to change in that circuit that will affect the statistics of the noise. But, naturally the assumption is that we're only interested in doing the analysis over a certain window of time, and we're just interested in what the statistics are in that window of time. For example, when the circuit is actually operating, something like that, at a particular temperature. So the sort of root mean square quantity is obviously going to be very useful to us. It's going to be a very useful tool. Another important definition we want to make is signal-to-noise ratio. It's a very simple concept that you've probably already encountered, but we want to make a rigorous definition of it because we're going to be using it so much. Signal-to-noise ratio, then, is going to be the ratio of the signal power to noise power, both normalized to the same impedance, and we're going to almost always express SNR in units of decibels, or dB. Okay. So if you like, you can think of the RMS quantity, as I said, as some kind of measure of noise power. Now, if we have that noise superimposed on a signal quantity, for example, signal superimposed on a sinusoid, then we can look for the power in the signal part, meaning the part of the waveform excluding all the noise, okay? And we already know how to compute the power in, for example, a sinusoid, right? The RMS value is just the peak value of the sinusoid divided by root 2. So then we can take the ratio of that quantity to the RMS noise quantity that we defined in the last slide, and we'll get an SNR value. So that's this ratio that's being shown here. Okay, and so here you'll notice that we're taking the ratio of the squared quantities. So in that case, we're actually taking the ratio of 2 powers, if you like, right? If we were actually taking the ratio of 2 powers in watts, right, then we would have to have this volt squared divided by a resistance, and then we would also have to have this noise volt squared here divided by a resistance, which would then show up in the numerator. And then you'll notice that's why here in the definition of SNR we specifically said that both the signal power and noise power are normalized to the same impedance. So in that case, the resistance or ohms that's this signal quantity is being divided by is going to show up in the denominator. The resistance that this noise quantity is being divided by is going to show up in the numerator. Those will cancel, and then you've just got these ratio of these volts squared. Now when you're taking the ratio of 2 powers and you want to express them in decibels, okay, take the log of them and you multiply by 10. That gives you the ratio expressed in dB. Note that dB is should always be a dimensionless quantity, right? So it's a ratio. It's a ratio of 2 things with the same units, if you like, and then we want to express it on a logarithmic scale. So that's what we use dB for. We take the log of that because maybe that ratio we expect that ratio to vary over a very wide range of values. So a linear scale's not as useful as a logarithmic scale. Take the log and then we just multiply by 10 to give us a nice number to work with. Now you'll notice, right, when you've got a logarithm and you've got this ratio inside the logarithm is actually squared, so we can take the squared out, take the squared term out, and we end up with 20 times the log of the ratio of the RMS voltage quantities. Okay, so that's a mathematically equivalent definition. But just know a lot of people get confused whether there's 20 in front of the log or 10 in front of the log. It depends if you're taking the ratio of powers or if you're taking the ratio of voltages or currents, right? Then, in the case of the powers, you've got 10 times the log. In the other case, you get 20 times the log. Logarithm here, by the way, is base 10. Okay. So that's units of dB and definition of SNR. Both really important quantities that we're going to come back to a lot. So now I want to define a unit of power. Okay, so I just mentioned when we defined SNR that the units of dB is a dimensionless quantity. It's always used to express a dimensionless ratio. So for example, volts over volts or watts over watts, dimensionless ratio on a logarithmic scale. dBm, on the other hand, is actually a unit of power. So for example, we will see that 0 dBm actually equals 1 milliwatt. Okay, so it's a unit of power. So how do we, get a logarithmic description of a unit of power? Well, here's the definition here. The units of dBm express an average power level on a logarithmic scale normalized to 1 milliwatt. So that 1 milliwatt is 0 dBm, 1/10 of that, 1/10 of a milliwatt is minus 10 dBm, and so on. So if you like, strictly speaking, right, if we're going to take the logarithm of a power, okay, we're going to take a power number, whatever it is, whether it's 172 watts or 13 microwatts, whatever the quantity is, we're going to normalize it with respect to 1 milliwatt. And it's the lowercase m in milliwatt that gives rise to the m in dBm. Right? So we're going to take that ratio, whatever the power is, with respect to 1 milliwatt. We're going to take the logarithm of that. Okay? And then we're going to multiply that by 10 because we're then dealing with power levels. So here's an example here. It's example 9.1 from the book. And the example is if we've got 2 volts RMS applied across a resistance of 50 ohms, let's express the power that's being dissipated in that resistor in dBm. Okay. So first of all, we see it's just straightforward arithmetic that the power being dissipated in the resistor is V squared over R, or 2 squared over 50 ohms, which gives us 80 milliwatts. Okay, so that's 80 milliwatts is the normal way to express power. Now we want to express it in dBm. We take that 80 milliwatts, we normalize it with respect to 1 milliwatt, take the logarithm of that, multiply by 10. It turns out that gives us 19 dBm. Okay, so 2 volts across a 50 ohm resistor, 2 volts RMS, I should say, across a 50 ohm resistor is dissipating 19 dBm. Okay. So this, as I said, is a useful unit for representing power, and it's the lowercase m that distinguishes this from the units of decibels, which is just a dimensionless ratio. Okay. And you'll see this trick a lot. You'll see dBV as a unit, dBA as a current, dBc sometimes. It's the extra letter added on after the dB is giving you a clue. It's giving you an indication of what the quantity is being normalized with respect to. For example, units of dBV you will sometimes see on a spectrum analyzer, for example. That's actually a unit of voltage. It's just taking a voltage quantity, normalizing it with respect to 1 volt, and then taking that, expressing it in decibels by taking the logarithm and multiplying by 20. Okay. RMS voltages or currents are also sometimes expressed in dBm by assuming they're applied to some agreed upon reference load. So usually either 50 or 75 ohms. So here again is an example 9.1, right? You can also think of 19 dBm as being a representation of 2 volts RMS, right? As long as it's somehow implicitly understood, somewhere stated, that you're dealing with a reference resistance of 50 ohms, right? As long as you know that you're dealing with 50 ohms, then you know that 19 dBm is equivalent to 2 volts RMS. So here's another example of dealing with dBm. Let's express 0 dBm, reference to 50 ohms in volts and in amps. So 0 dBm, right, is just equal to 1 milliwatt. Because that's like taking the log of 1 milliwatt over 1 milliwatt gives us 0. That's all that's saying, right? So 0 dBm is 1 milliwatt. 1 milliwatt, reference to 50 ohms, right, must have a RMS voltage that's equal to the square root of 50 ohms times 1 milliwatt. Okay, so the square root of 0.05 is just 0.224 volts RMS, or 224 millivolts RMS. This is an example that's good not just to give us some practice in dealing with dB, units of dB and so on, but it's also good to have these sort of numbers at the tip of your fingers. 0 dBm, right, is a nice reference point, and it's a nice round number that you may encounter often. And so now you know if you've got 0 dBm, 50 ohms, then that must be 224 millivolts RMS. Also, once you can work off that number, if you can memorize that number, right, it saves you having to punch logarithms into your calculator. You got that number memorized, 224 millivolts. You also know that if you're dealing with 6 dBm, you must be dealing with twice as many millivolts RMS. So it'll be about 450 millivolts RMS, and so on, right? If you're dealing with minus 6 dBm, then you're at half that, so you're at about 110 millivolts RMS. So, you can impress your friends this way at parties by doing these logarithmic calculations quickly in your head. You're really just starting from a reference of 0 dBm and working off that. How much current RMS is that? Well, we know that the volts RMS times the current RMS must equal the total power, which is 1 milliwatt in this case, and then we can just rearrange that to find that we must be dealing with 4.47 milliamps of current passing through a 50 ohm resistor to give us 0 dBm of power. And we can just do a sanity check on that, right? We can confirm that Ohm's law is being followed just by checking, make sure that the RMS voltage equals the RMS current times the resistance. And I'll leave that for you as an exercise, but indeed it checks out. Last thing I want to touch on here is the concept of noise summation. So we've talked a little bit about what we can say about a noise current or noise voltage in a circuit, right? We can't say much about its specific value at a point in time, but we can capture information about the average power carried in that noise quantity, right, by using the idea of RMS quantity. Now, what if you have two noise voltage sources appearing in series? And this will happen all the time in sort of practical circuits that we deal with. So we're going to use this symbol here, the circle with a sort of star in it, to denote an RMS or a noisy voltage source. Okay, so it's a little different than a usual, independent voltage source symbol that we would use, where we might have a polarity indicated on this circle here, on this voltage source. With a noise voltage, I mean it's, we can't really define its polarity because it's bouncing all over the place at the time anyway. So that's the idea of using this star here to denote a noise voltage source. So in here we've got two of them in series. And what we're interested in is what's the resulting noise that appears over here. Now, regardless of the fact that VN1 and VN2 are noisy and that they're random processes that are bouncing all over the place, that doesn't change the fact that two voltages stacked on top of each other must add. So at any given point in time, the total voltage at VNO must equal the sum of the noise voltages VN1 and VN2. Okay? So there's nothing fancy there at all. There's nothing, no difference in the concept of superposition. What is different, of course, is that we don't know what VN1 is. We don't know what VN2 is. We don't know what VNO is. The best we can do maybe is we can figure out what's the RMS value of VNO. The RMS value of VNO must be given by this, integral, right? We sum up VN1 and VN2, and we take that squared, integrate it over a window of time, 0 to capital T in this case, okay? And we get that average squared integral, okay? Now, when we expand out this term in the squares here, right, we've got VN1, we'll end up with the integral of VN1 squared, okay, that's just VN1 RMS squared. We'll also get another term that's the integral of Vn2 squared. That's just Vn2 RMS squared. And then we end up with a third term that's the cross product of these two, right? 2 times Vn1 times Vn2. And then we integrate that. Now this we know less about, all right? Because this is like a cross correlation, all right? Remembering back to your probability theory. This is like the cross correlation of these two noise sources, Vn1 and Vn2. Now, what is the cross correlation between those two voltage sources? Well, it depends. If they're both arising from the same underlying physical process, for example, maybe they're both modeling the random motion of carriers in the same resistor somewhere, or something like that, okay? Then certainly they'll be correlated, right? Because they're both voltages that are arising from the same underlying process. But the more common case that we're going to deal with is where Vn1 is arising because of some noise in one device, Vn2 is arising from some random motion in some other device, and those two the noises contributed by those two devices are completely uncorrelated. They have nothing to do with each other. So if we're summing together two uncorrelated random noise signals, then this cross-correlation term will work out to 0. Okay? And it'll just disappear. And then what you see, you're just left with VNO RMS is just the squared sum of VN1 RMS and VN2 RMS. So that may seem not too surprising, okay, at first, but it's in an important way very different than superposition of two independent voltage sources, right? For example, if we had 1 volt here and 1 volt here, we would of course have 2 volts at the output here. That's the sort of normal superposition that we're used to. But if you have 1 volt RMS here and 1 volt RMS here, and you also know that those two are uncorrelated random noise sources, okay, then you don't end up with 2 volts RMS. You end up with root 2 volts RMS, or about 1.4 volts RMS at the output there. Okay, again, this may seem like basic arithmetic to you, but it's a very important distinction. We'll see. I think the example that's coming up next will illustrate it very well. Same results, of course, apply to noise currents that you would be summing. And when do you sum currents? Well, when they're connected in parallel, right? So if you've got 2 noise currents coming into the same node, then the noise leaving that node, the noise current leaving that branch there, is summed together in the exact same way. Assuming IN1 and IN2 are uncorrelated, you just end up with the root sum of squares noise current here, RMS noise current there. Okay. So why is this concept of, this funny kind of superposition of independent noise sources important? Well, let's consider this example here. Okay, if you've got 1 millivolt RMS in series with 5 millivolts RMS, if you work through that, right, you're taking the sum of these 2 quantities squared. 5 squared is 25, 1 squared is 1, sum of them is 26, and you take the square root of that, and that's the RMS quantity that you'll see here. The square root of 26 is just a smidge over 5. So the interesting thing is you've got 5 millivolts RMS, noise source here, and another 1 millivolt added on top of that contributes hardly any extra noise. You basically see something like, I don't know what the number is, 5.1 millivolts RMS or something like that here. This is very interesting. What it means is that if you have 2 or even more than 2 noise sources that are being superimposed, it turns out if one of them is even, by any significant amount bigger than the others, it will completely dominate the others because of the way the superposition happens as a sum of squares instead of just a straight sum. The sum of squares will tend to emphasize the largest of the noise sources much, much more than when you're just taking a linear superposition. Okay? So what this means is when we're dealing with noise, when we're analyzing noise, we will see that, really it's the 1 or maybe 2 dominant noise sources that are really all we have to worry about, because they will very, very much dominate over all the others that are being superimposed on it because of this, the fact that they're uncorrelated, basically, means that the contribution of VN1 in this case will be very, very small on average. So that's the key point. I encourage you to work through this example here and some of the problems as well for section 9.1 to help cement these ideas, and then we can go forward. Thanks very much.